Thanks everybody for coming to this morning session of talks. Here, Dmitry will talk about an optimal space lower bound for max cut.
Welcome everyone. Thanks for coming. I will be talking about a paper I wrote together with Michael Kapralov back in 2018. I should warn you that this is not my main area of expertise, or it's not exactly what I'm doing now, so forgive me if I say something which is either stupid or well known to everyone, and sort of let me know in which direction to go. Let me start from describing what the problem is. I will first start with describing the model. So the model we work with is streaming model. So more classically, when you run an algorithm, maybe most often you care about the time complexity of your algorithm, so you want your algorithm to be fast. In the streaming of model of computation, what happens is the information arrives to you in a stream, and you don't worry so much about the time it takes for you to do the computation, but you worry about the total storage you're going to use to process the data and then output the result. So in our case, we are going to be working with graph, and so our streaming is going to consist of edges. So you may think that the set of vertices is nowhere and edges arrive in a stream. We use as little storage as possible. And at the end of the stream, you want to output the result. Output the function. Also, we will allow our algorithm to be random, so you have internal randomness, and you only want your result to be correct with some probability larger than 1. Okay. So this is the model. So we are only going to work with simple graph, no loops, no double edges, nothing like this. So what is the problem that we are going to be looking at? This is the problem of approximating max cut. So what is max cut? Given a simple graph, something like this. The max cut is just the maximal number of edges you can cut by partition of vertices. So here you can, for instance, split the vertices like this, and then you cut all edges but 2 of them. Here it's easy to see that it's optimal because you have 2 triangles. Okay. So the problem now as follows. You have the streaming model of computation, you have a graph, you have n vertices, m edges. Edges arrive in a stream, you store small amount of information, and you want to output the max cut. Okay. So the final thing we are going to allow ourselves is to be not exact with computing the value of max cut, but we're only going to be caring about an approximate value of max cut. So we say that alpha approximation is an alpha approximation if the max cut value is between C and alpha C. Okay. So we have streaming model, we have randomized algorithms, and we want to output an alpha approximation to max cut using as little storage. So let me first mention to you a bit about the max-cut problem in a classical setting. So when you care about time complexity. So classical setting for okay. So first of all, computing max cut value exactly is NP hard. So
and if you restrict to planar graphs?
I would think that it's not NP hard.
Okay, just
So it's in the streaming model, is it like online? So do we want to maintain an approximation to the?
No. You only want to output the value at the end.
So how does those ages come in? Random order or?
No, it's adversarial.
So is it like multiplicative? Do the hardness in the algorithms have a multiplicative guarantee, or even for like additive guarantee, it's still easier or harder or something like that?
By multiplicative guarantee, you mean this? I mean, additive guarantee seems too hard. It's like almost like exacting up to like a few edges.
And also, do you care about computation time, or it's just?
No, so we forget completely. Partially because of this. Also, I guess if you want to maintain, you can just compute it for like different scales. So it's not going to change the problem much. Different scales of the number of edges. Okay. But in fact, even approximating isn't hard. So famously, the possible alpha approximation for the time for alpha, which is like 1 over 0.87 something. So if I remember, alpha is 2 over pi. Let me check the formula. Theta is by different alphas. So this comes from certain linear programming problem. This is by Cummins and Williams. And also assuming Unix game conjecture, it says something to you. This is Berthold's law. So it's possible to approximate this in polynomial time, but not better. But without any assumption, we know that 17 over 16 approximation is an right. So again, in our setting, we completely forget about the time complexity and we only think about the space complexity. Okay, so let's try to understand a bit about our problem and what approximation is possible. So there are basically two extremes in this problem. Back to streaming. So first extreme is when your approximation factor becomes 2. So if alpha is at least 2, then m over 2 is an approximation. Because max cut value is clearly at most the total number of edges, and also max cut is always at least one half of the number of edges. The easiest way to see it is just to take a random cut. So if you uniformly partition vertices at random, then you're going to be good. If anyone wonders, the correct thing is this. I mean, you can tweak it a bit above the random thing. But there are graphs with this. Okay. Which means that if you only want to do 2 approximation, then you don't need to store that much of the graph. You just count the number of edges, output the thing, and so it's going to be log n. Okay. So you have 2 approximation in logarithmic space, and what is the opposite side? So if you want to store 1 plus epsilon approximation, then one thing you can do is you can store subsample of your graph. So you take every edge and retain it with constant probability, so that the total number of edges you retain is roughly linear in n, with constant depending on epsilon. So store roughly n log n edges and compute. When I say compute max cut, I mean, so you subsample the graph, compute max cut, and then multiply the max cut divided by the density of edges you retain. And it turns out that this is going to be a 1 plus epsilon approximation to max cut. This is just some concentration bound. Basically, every cut is going to be multiplied roughly by the density of edges. You can show that max cut is going to be also multiplied by that. Okay. So this means that even if the number of edges is much larger than the number of vertices, it's still always enough to have linear space in the number of vertices to get arbitrary good approximation. So here we are not going to care too much about the logarithmic factors. Partially because, I mean, realistically, this is the question of how you store vertices and things like this. Okay. Sorry. Here I meant n of epsilon squared edges. It's just that the space that we use is n log n of epsilon squared, because maybe you will use like log n bits for each edge. Or maybe you can do smart. So for n log n epsilon squared. Okay. So the natural question becomes if there is anything in between that. So what is the trade-off between the approximation factor and the space complexity? The question. So it turns out that that's with no. So let me state the theorem that we proved. And then I will comment on what was known before. So it turns out that once you depart from 2 approximation, then you cannot do better than the linear space. So any randomized algorithm computing cut given minus epsilon factor with probability larger than 1/2 must use at least linear space. This probability, I guess, larger than something bounded over 1/2. Okay. So let me mention what the dependence on epsilon is. It's not so interesting for the problem itself because it's probably very far from optimal, but it's optimal for the communication problem that we will be essentially solving. So there, it was originally this, but then it was something like this. Again, I don't really know and even believe that such a huge factor is needed for the original problem. But it seems that for natural communication problem that arises, this is the correct answer. Okay. So let me mention that this wasn't the first work on Max Cut in the streaming setting, and in fact our approach was used before. So the general outline of the proof, at least the beginning of the proof, was known before. So before that, the results which were known were that you always need, I'll just say it in words, you always need square root n space if you want to do approximation better than 2. And also it was known that if you want approximation which is very close to 1, then you do need linear space. This is basically the two results which we need. And partially it already suggested that maybe this should be true. Okay. Right. So let me now tell you how you would approach this kind of thing. So maybe first thing to realize if you're just thinking about the problem is that you need to argue about arbitrary algorithms. Now you don't have any time constraints. And a very sort of natural way to do it is to reduce the problem to certain communication problem. Typically, let me maybe before saying the problem to which you're going to reduce this, I will tell you the reduction, which will explain roughly what the problem should be. So typical reduction is you have two players, and the first player is going to run first half of the algorithm on the first half of the stream. Then this player is going to send the current state of the algorithm, which is supposedly small if you use very little space, to the second player, and then the second player is going to run the algorithm on the second part of the stream. So the communication problem is typically one player gets one half of the graph, second player gets the second half of the graph. Okay. So it turns out that in this particular setup, having two players is not so good because so roughly speaking, what you want to do is you want to partition the edges of the graph into parts such that each part is bipartite or roughly bipartite, so that each player individually can't really see that the graph is far from being bipartite, right? So 2 minus epsilon factor means that you want to say that it's impossible to distinguish a graph which is very close to bipartite to a graph which is as far from bipartite as possible. But if you only have two players, then each part being bipartite is going to tell you that the union is also not too far from being bipartite. That's why we are forced to consider a communication problem where we actually have many players as opposed to two players. Yes?
Is this problem also tied if you have in the multipass model? You can see that.
No, I thought about this for a bit, and it's much harder. I think something appeared after our work, but they don't get. I mean, the belief is clearly that it should be still linear if you have constant number of passes. But I think what they prove is maybe they prove square root n, but I'm not sure. Okay. So having this in mind, let me tell you about the communication problem. So the communication problem is called implicit hidden partition. Okay, so what is the problem? So we are going to have T players. I'm going to right away sort of match the constant from the original problem. So T will end up being roughly 1 over epsilon squared. T players. So each player gets a matching, alpha n size matching, MT. So it's going to be, so for notational purposes, our matching is going to be written as alpha n by n matrices, where we just record incidences of edges and vertices. So each row is going to have like 2 1. This is easier in order to then multiply by vectors essentially. So alpha here is just a tiny one. Alpha is constant. Okay. So each player gets a matching, and then on the matching, we are going to also record bits 0 and 1, which are going to correspond to whether we want this edge to be crossed in the bipartition or not. So, as well as omega t in 0, 1, alpha n stable. Okay. So now we have the T players. The communication is going to be sequential, meaning that the first player is going to speak, then the second player is going to receive the message from the first one and is going to publish its message, etc., etc. So they don't communicate arbitrarily, but sequentially. So MT are public, omega T are. So what this means is that once the player gets the matching, the player gets to just put the whole matching on the board, but omega T is only visible to the player.
Alpha n size matching means?
Oh, so it means matching of size alpha n. So it's like a collection of edges. Alpha n. Okay. And so
omega t. What is it?
So omega t are labels on, so each edge gets to have label 0, 1.
Oh.
So T's player.
Sorry, the 0, 1 means whether they're in this next cut or in this approximation cut.
So these zeros and ones are eventually going to correspond to, so we will want to find the bipartition such that all edges which get 1 are crossed by the bipartition. So the two verses are in different parts, and everything with 0 are in the same. So T's player posts a message as T, which is a function of of what? Of all the matchings before, as well as all the messages before and the bits. So this is the information available to the t-square. Okay. I mean, RT is just a function. So the rules of the game are that the last player wants to output yes or no, depending on whether there exists a bipartition consistent with labels. So the last player wants to output a function of all matchings and labels, which is equal to yes if there exists x in 0, 1 to the n. So these are labels such that omega t is mt times x. And you see, and no. So when you multiply the matching, which is given by a matrix, by the labels on the vertices, you exactly get the labels corresponding to whether the edge is crossed or not. Right. What?
Is that a total function, or do you have any promise on the no instance?
Sorry, say it again?
Is there any promise on the no instance? Like even on one bit for one player, if it's not correct, should the output no?
Yes, I mean for now we don't have any like distribution of the inputs, so we just want to understand whether it's yes or no.
Okay.
But for the reduction, we will have the sort of distributional version of this, where in the no instance it's actually going to be far away. Right? Because for now it's possible that no instance is very, very close to the Okay. I'll just use this. Right, so in order to do any kind of reduction, indeed we want to have some distributional inputs such that when you have no instance, then the situation is very far from the yes instance. So the good source of no instances which are far from being bipartite are random instances. So if you have enough matchings, which is here 1 over epsilon squared, then if you start writing bits on these matchings at random, then there won't be any bipartition which matches this. It's very high probability. So the distributional version implicit hidden partition, DIHP. So the distribution is 1/2. So with probability 1/2, you draw the graph from yes instance and with 1/2 from no instance. So what is the yes instance? Yes instance is going to be the following. You first sample the bipartition of vertices. So yes. So x star is in 0, 1 to the n, uniformly random. then you sample all the matchings again at random and see IID uniformly random alpha and matchings. And then, because it's a yes instance, you just write the labels corresponding to X. On BT. What is the no instance is empty at above. So the matchings are still uniformly random, but now WT are also uniformly random. So notice that formally this is not necessarily a no instance, but with high probability it's no instance, which is just like a union bound over. Okay. So now let's do the reduction. So notice that here, as opposed to what I described to you previously, we don't just partition the graph, but we get to have this additional layer of complexity, which are the labels. So now somehow we, apart from having edges of the graph, we have like anti-edges, which we don't want to be crossed. I think that part of the reason for this is that here the edges themselves of the matchings are public, right? So if we didn't have labels, there wouldn't be anything to communicate at all. And it turns out that it's, I mean, probably the same would work if we just had edges and didn't have labels. And the matchings were sort of private. But it's much harder to argue about communication of information about matchings rather than communication of information of like uniformly random bits. Just because the space of the bits is the boolean cube, and this is sort of the topic of the semester, that sort of on the boolean cube you have a lot of structure to argue about the communication of information, as opposed to whole set of like alpha and matchings. I think the reason for this. Okay, so reduction. What is the reduction? So theorem. So in which direction? So if this is hard, then 2 minus epsilon approximation is linear space. So, I mean, I'm not writing all the details here. So in the distributional version, so the graph is drawn from this distribution, and the last player should understand whether it's in yes or no instance with probability at least 0.51. So the claim is that if you show a lower bound for this, then we will show 2 minus epsilon bound. So proof. So of course we want to argue in the opposite direction. If there were a streaming algorithm, we would want to solve this problem. So assume 2 minus epsilon approximation for max cut is possible in sublinear space. So now we want to do the same thing I described before, but we want to only look at the edges which get labeled 1. So each player runs the streaming algorithm on the part of the graph obtained by looking at edges with label 1. Looking at edges. And so the last player, to understand whether it's a yes or no instance, looks at the result of the algorithm and says yes if the value is close to the total number of edges. So last player says yes if max cut approximation is 2 minus epsilon close to n. Okay. So here, in order to show that this reduction is valid, you not only need to show that the no instance is that this part of the distribution is supported on no instances with high probability, but you want to show a stronger thing that if you look at the edges, we get 1, which is basically a union of alpha n over 2 size matchings, then this graph is going to be very far from bipartite. Right? So you want to say that the algorithm which gives you the approximation is going to distinguish this case from the bipartite case. But that's again not so hard. So if you have like 1 over epsilon squared, roughly, matchings of size constant n, then it's easy to show that the union is sort of close to a random graph in the sense that the max cut value is going to be roughly half of the edges. The proof is again just union bound over possible bipartitions. It turns out that the concentration is good enough that you can just, for each bipartition, show that the number of edges crossed by this bipartition is roughly 1/2. Okay. Right. So this is the reduction. So now the question is, what you do with this distributional implicit hidden partition thing.
I just ask, sorry for being confused about this, but what is the actual communication protocol? So players in turn, like what information do they wish to hear from the previous player?
So they just send the state of the algorithm, right? So the algorithm is doing something, then it stores some amount of information. The algorithm is like a public thing. It's not
okay, so they send the entire
state of the algorithm.
Okay.
Like the whole storage. And then the next player just runs the algorithm, whatever the algorithm is.
Sorry, can you go to the previous board a little bit? In that sense, if T's player posts a message with last indices is omega T, then the next player will only receive omega T from the previous player, right? How do the last player get omega 1 to omega T? All of them.
I mean, that's the problem, right? So even though you communicate less information than everything which is known, you still want to compute a function, right? So of course, if the amount of information sent could be linear, then everyone just sent everything, like all omega T. And the question is whether you can compress the information and send less than everything about omega t, such that you still recover the function of everything.
I think the thing I don't understand is, like, what does an ST mean there?
ST? ST is just like a string of bits that the player sends.
The T's player sent to the T plus 1
Yeah.
player. Then the last player will only receive omega of T minus 1, right?
Yes.
So T, like, last player don't have the information of omega 1 to omega T minus 2.
Except for the messages. Yeah.
Except for the message.
All of the messages, right?
Yeah,
All of the messages are public. S1 through SK
Are all public.
are all available to SK plus 1.
So this doesn't matter because every player can like repeat the previous message. It's not.
Okay. Oh, because you said omega T is private, so
Yeah.
in this sense, like omega from 1 to T is all public to the last one.
No.
Sorry.
It's the messages which it retains, right? So the omega t is like linear space. It takes alpha n space.
Yes.
And the whole question is whether we can compress this information by sending only some sort of snapshot, like part of this information, so that at the end we can still recover the function. Of course, this very much depends on the function f. So some functions of the graph are easy to compute in small space, some apparently. Of course, given linear space, everything would be trivial. The question is whether you can do that.
So it's the last pair want to output this
Yes.
function.
Yes.
Oh, okay. It's not his input, it's those arguments.
Yeah.
Okay.
Yeah, f is like argument.
Thank you.
So let's try to analyze. I think we will show that if you have much less than linear space, then you can't get the answer with probability better than like a random guess. So you take S, which is like n over the target thing. You take S prime, which is for n. Maybe it doesn't matter. So S is the amount of space each player gets. So ST corresponds to AT prime 0, 1 to the alpha n. So each message, because we don't know how the message is formed, the only thing we know is the pre-image of this message on the space of labels. So essentially each player, when player says this message, the thing we have in mind is the subset of the hypercube of this hidden information which corresponds to this message. Of possible labels. So the thing we know is that typically, for a typical message, this subset is going to be large. So typically, okay. So now what happens with the propagation of information about the whole thing? So we are going to be analyzing essentially the guess case And what we will be showing is that the players are not going to be able to distinguish yes case from the no case, as in they're going to see everything very close to the no case. So, let AT be set of x in 0, 1 to the n, such that MTX is AT prime, and BT is A1, etc. AT. So we have a message corresponds to possible labels, and possible labels correspond to possible labels on the vertices, which are consistent with these labels on the edges. And when many players spoke, we know that the possible labels are in here. Once the set becomes empty, the player can instantaneously say, then we are in the no instance, and like transmit this information. So we will want to be showing that this thing is never empty. But of course, if you want to do some kind of induction, you want much more than that, because you want to say that the set BT is such that whatever information, sublinear information, the next player sends on the matching, it can't be reduced to an empty set. Like it's not possible to, by using information on Q matching, somehow rule out all the previous possibilities for the labels. Okay. So essentially, the propagation of information is going to be that the next player, the T+1 player, is going to know that the labels are from this set, BT. And you need some sort of induction hypothesis which is possible to propagate further and further. Okay. Right. So what is, our induction hypothesis? There are going to be like several parts of it, but the most important part is going to be based on the Fourier spectrum of the indicator of that. So let's first do the sort of part which is sort of more general, and think what we know about the Fourier spectrum of arbitrary subsets of cube. So here, the subsets of the cube, you should, like, one of the hypotheses is going to be that this set is large, right? Because once this set is very small, it only has like 5 vertices, then it's kind of easier for the next player to rule out the whole set. So you want to show that in particular, so one of the hypotheses is going to be that BT is roughly 2 to the n minus st. So basically each time it gets reduced by roughly 2 to the minus s. Okay. So what do we know about the subsets which are large? So the basic thing is what's known as KTL inequality, also known as hypercontractivity. Let me maybe just right away write the bound that we want. I mean, there are like different forms which are all sort of equivalent. So the bound that we are going to want is if A is 0, 1 to the m, and the size is at least 2 to the m minus d, then 2 to the m squared is at most, I think, 14. So here we sum the squares of Fourier coefficient on level q. So level q is at most d. So this inequality tells you something about layers up to d, where so d, a is 2 at least 2 to the m minus d, which corresponds to roughly sending d bits. So let me mention in words. Hypercontractivity comes from the fact that the typical proof of this and related fact is that if you take a function and you apply noise to this function, then you can bound higher LP norm, like LQ norm, which of the LP norm of the original function, if the noise is like small enough corresponding to the discrepancy between P and Q. That's probably the shortest proof. But I think here it's helpful to think about this in terms of the sort of information. So if you write sort of normalized Fourier coefficient as this, which is going to be the expectation of x, so z uniform in A minus 1 of t, then this inequality is going to be the sum of the squares of normalized Fourier coefficient is at most this. And this should be thought of, so the square of Fourier coefficient. If Fourier coefficient is epsilon, then it means that for uniformly random point, the XOR of the bits is going to be like Bernoulli 1/2 minus epsilon. So it's like,
You forgot F, right?
yes. Okay. No, I didn't. It's expectation of a uniform
Oh, yeah,
point.
it's just
Yes.
characteristic function.
Yeah. So, okay, Bernoulli is not the correct thing. It's like 1/2 minus 1 and 1/2 plus 1. But the thing is that the information, so the entropy of the distribution is roughly epsilon squared. So the square of the Fourier coefficient should really be thought of how much information do we know about XOR of the bits. And if you just send d bits, then you're going to have roughly d over q q tuples no one exactly. Right? So this corresponds to a subset of the cube where some bits are fixed. And KKL says you can't send more. Right? If you have a subset of this size, this really corresponds to sending at most q bits in the sense that on average among like XOR of q bits, you're not going to send more information to them. Okay. Okay, this. Right. But here, like in our thing, it is important to know more about the BT, right? Because it's possible that even if you send like much less information, but somehow the information that you got is correlated with a new matching, then the next player is going to learn the whole thing. So in particular, one thing which is important to rule out is even if you restrict to like plain text messages, so messages are not allowed to be convoluted, but all the messages are only labels on edges. And the typical way to understand that you are in a no instance is to find the cycle. So once, if players post plain text of the labels on edges, and it turns out that the union of these edges form a cycle, then you can just XOR all the bits on the cycle, and if they get 1, you understand that it's not consistent with any bipartition. So, in particular, you need to show that it's impossible to find a long cycle by posting subsets. You can actually analyze this naive algorithm where each player just posts like a random subset of the matching, and then you will find that union of that is not going to contain a cycle. But moreover, even if you do it adaptively, the next player posts all the edges adjacent to the edges posted by previous player, and you can analyze the growth of this connected components, and you will find that your very unlikely to find a set. But of course, in general, it's more complicated because you can send information about all the edges of your matching, but like small amount of information about each edge. And KKL inequality quantifies this fact. Like if you send something about all the edges, then you receive little information about each edge. So let's think about B1. So B1 is equal to A1 is equal to the possible labels corresponding to sets, possible labels on vertices, such that when you XOR, you get the labels on edges in the subset. So let's think for now about like the plain text. So you say you know that these are 1, 0, 1 or something like this. So the set is, okay, this is x1, x2, x3, x4. So the set is x1 XOR x2 is equal to 1, x3 XOR x4 is equal to 0, x5 XOR x6 is equal to 1. Something like this. It's easy to see that the only Fourier coefficients which are non-zero here are those formed by union of pairs of these bits. Because if the Fourier coefficient has x3 but doesn't have x4, then it's 0. Right. So indicator of B1 hat of B is 0 if B is not matched. By F1. So if you don't have the structure of bit and the opposite bit on the matching, and otherwise it's going to be indicator of A1 prime hat of, let me write V over 2. So we have A1 prime, which is subset of the 0, 1 to alpha n, this subset of labels, and it's easy to see that if V is matched by the edges, then you recover the Fourier coefficient of that subset of the cube, but now you have twice less the level is twice smaller. Right? So in fact, for the message B1, when you apply KKL, you get a bound which is much better. Right? So for B1, sum over Q, sum over X equal Q, B1 hat of X. If this is normalized, squared is at most 40 over Q over 2 to Q over 2. And only even levels matter. Okay. So essentially the idea for the induction hypothesis is that something similar should be true when you combine the messages. The question is how to make it robust enough. So the problem is it's not going to be literally true that you're only going to, like if you write this hypothesis, it will turn out that it's not going to work. So in fact, like let me maybe explain. So the important thing here is actually to get a bit like L2 bound on the level Q. You also need to show that it's impossible to somehow say a little bit about the whole level. So your enemy is going to be that you have the correct L2 bound on the level 2Q, but now you know everything. You know a little bit of information about each Fourier coefficient on level 2, which is not true here, right? So here, you have only n choose Q over 2 non-zero Fourier coefficient at level that's additional feature together with this. So after two messages are combined, this is not at all true anymore, because basically if the first player says something about bits on this thing, then the second player gets some so basically the messages of two players, when they're combined, they're now going to be supported on all possible sort of vertices which can be matched in pairings by the union of two matchings. And once you have like 10,000 matchings, you know that the graph is random, which was important for our analysis because we know the resulting graph to be almost close to random. So by the end of the procedure, you're going to know something about Fourier coefficients which are almost arbitrary, because almost arbitrary set of two Q vertices is going to be matched by the edges. So it turns out that the sort of stronger, not stronger, but the correct way to formalize the fact that you are sort of supported on much fewer Fourier coefficients is to bound L1 norm rather than L2 norm. So till when do we have time?
Well, we started 5 minutes late, so 15.
So let me write this intuition level 2L as n choose L non-zero Fourier questions. So this is not correct after many players spoke, but we should be guided by this thing and write L1 bound as if this was true. So the definition is B subset of 0, 1 to the n is CS bounded if for any L smaller than S prime. So S star was something intermediate between S and N. So it's still slightly sublinear in N, but much larger than the size of the messages. So sum of so it's always true that you're not going to have all coefficients on odd levels are going to be 0 by like flipping the thing. So on even levels, if you look at the Fourier coefficients, then this is going to be at most C squared plus M over L. So this is the bound which would come from Cauchy-Schwarz if the number of non-zero elements was of order n choose L. But here we only look at the level which is smaller than S prime, S star, and if you do induction, of course the next thing, so let me write it here, so BT is like, the indicator of BT is going to be indicator of BT minus 1 times indicator of AT. So when you want to bound the Fourier coefficient, you're going to use the convolution theorem, right? And in convolution theorem, what's going to contribute to levels smaller than S prime are also levels larger than S prime. So you kind of also want to incorporate some bound on the level larger. KKL says nothing about the bound there for a good reason. There are no non-trivial bounds. But you still want to maintain this hypothesis that the number of coefficients is small. So the bound you write there is that for L smaller than something which is much smaller than N, you have is it C squared times 1? So again, this bound would come from trivial bound on L2 norm, but if you only have n choose L Fourier coefficient as opposed to n choose 2L. And this is sort of important in order to push the induction hypothesis, because eventually, of course, we use convolution and we need to bound on all Fourier coefficients of that. Okay. So basically, let me write like the outline of the proof. So proof outline. So the first thing to show is that V1 is V star bounded. This I essentially already told you how to prove. You take KKL for A1 prime, and then you notice that level 2L for V1 corresponds to level L for A1 prime. And then you use Cauchy-Schwarz. That's how you prove this, and more importantly, how you come up with this definition. So the second thing, which is important, is that you need to show that actually this boundedness implies the fact that you don't learn anything about typical matching. So if B T minus 1 is prime bounded, then MTX condition on X being in BT minus 1 is close to uniform for most MT. So of course there could be a matching such that it's not close. For instance, if somehow this matching closes a bunch of cycles. But for a typical matching, you can show that in total variation distance, each player is going to see uniformly random. This is part of the intuition that like it's indistinguishable from the no case. And so what is other facts? So another thing is that BT is going to be at least into the n minus st minus u of t. I mean, it's roughly going to be each time exactly cut by 2 to the s parts. All of this is, of course, with high probability over. And the last part is that you want to propagate the information about the boundedness. Of course, it's not going to stay like 3s prime s star bounded, but the constants are going to get exponentially worse. So roughly BT is MC to the T TS prime. So somehow each next player when it speaks, then the next player gets like a bit more information, and the bound on the Fourier coefficient becomes a bit looser, but it's still only a constant, right? So eventually the last player is going to see B capital T, which is constant as prime bounded. And so the information about the labels, the like posterior distribution on labels, is very close in total variation to uniform one, which means that the last player cannot guess the answer, like distinguish the guess case from nose case, with probability larger than this total variation bound. Okay. Let me finally mention that, I mean, the longest part is, of course, showing this. So you basically want to show a lemma, which is the induction step. Like, if BT is C as bounded, then for most matchings, once you combine BT multiplied by the indicator function of AT, which comes from some AT prime, then the new thing is going to be again CS bounded, but the fact that the proof is long is mostly from the fact that this definition is long. So you need to bound separately the low-level Fourier coefficient, which are going to be split into 3 parts, because in the convolution theorem, you are going to have some information from, again, low levels, you're going to have from intermediate levels, and also from higher levels, which you don't have any bound. And so you kind of need at least 6 cases. Like you need to look how information goes from either low, intermediate, or high levels to either low or intermediate levels. So that's why the analysis is like complicated there. But I think I basically described the whole intuition. Okay, thank you very much.